All right, I am live. So, thanks for joining. You can see I've already got the thing running. I've been doing some testing today. For anybody who doesn't know what this thing is, the Graviflyer, invented by Alexey Chekurkov, Russian inventor. He, over the course of about a decade, ended up taking ideas from Graviflyer and Schauberger and Tesla and a few others in order to come up with this idea of a craft, and he ended up making a bunch of videos over the years that showed it flying. He ended up doing live demonstrations with me and my team over Zoom and multiple times, and we were able to see that the thing was actually flying. So let me fix my mic here so maybe it's a little easier to hear me. There we go. Yeah, so live demonstrations over Zoom with the team. So, you know, as far as anybody who wants to say things a big old hoax and he had strings and all that, no, I can tell you, hand over my heart, hand God. From what I saw over the Zoom meetings, the thing looks absolutely legit. So the way the thing works, you got a piezoelectric buzzer on top that's operating the ultrasound range of 20 kilohertz to 100 kilohertz. You got a clockwise spinning disc for the top that is charged to a positive high voltage from a flyback. And then you got a center disc that is charged with a Tesla coil to about a couple kilovolts AC, peak to peak, at about a megahertz, give or take, for the fundamental frequency. The bottom spinning disc spins counter to the top. So this one is going counterclockwise. It is charged to a high negative charge from the flyback, same flyback. Yeah, and by tuning all of these things together, Alexey is able to make this thing fly. So this is my attempt at making the thing fly just like he did. So right now, for the testing that I'm doing, I have set the distances, which is a very key ingredient, is the spacing of these two spinning discs. I've set them so that there is a 4 millimeter difference in the spacing between the top and the bottom for the distance from the magnets on the bottom disc to the center versus the distance of the top disc to the center. The reason why I've done that is because my Tesla coil is currently running at about 4 kV peak to peak. The rule of thumb is you got 1 kilovolt per millimeter. In Alexey's crafts that he sent us, the spacings were different on the two he sent us, but in both instances, it was a 2 to 3 millimeter difference in the distance between the magnets to the center and the top disc to the center. So I suspect, my guess is that spacing might be necessary because he is offsetting the difference between the high voltage charges on the spinning discs and the Tesla coil charge on the center disc. So right now I'm playing around millimeter by millimeter trying to see where does that sweet spot overlap. Hey, Charlie. So on my spectrum analyzer over here, I have it set 0 to 50 megahertz, and you can see these spikes traveling down along there. The direction of those spikes will change depending on my zoom level. But those spikes are related to the beat frequency, the difference in speeds between the top and the bottom. And you can see that top disc kind of, every once in a while, it does a little wobble thing. Well, that wobble is related to the eddy current that's being created by the spinning magnets in the center disc. And as you get the thing in or out of resonance, that wobble will increase or decrease. Well, that wobble, that beat frequency, that eddy current going all over the place, that's what's responsible for all these spikes going across my scope. If I zoom out a little more, now you can see they're going really fast the other way. This is 0 to 125 meg. And actually, these spikes, they go way high. This is 0 to 350 meg. And I don't know how well you can see that on the... You can kind of see that on the camera. Those spikes, sure, the amplitude's way low, but they propagate really high in frequency. I don't know how important the high frequency parts are, but I have a pretty good idea that down here in the lower frequency regime, where all of my Tesla coil frequencies are, that's probably an important area. Now, I can try to get these things to stand still by making slight tweaks to the speed of the discs. Right now, I have both discs running off of the same motor controller. So just one small tweak here affects both discs. If I tweak this just a little bit more, see if I can get those spikes to kind of stand still. They're kind of standing still a little better. They'll probably start going back the other way as it changes speed. But what I've found today is I already knew that the ultrasound can affect this beat frequency, and it can affect the speed of the discs. Oh, by the way, right now I don't have any high voltage DC from the flyback on the discs. Right now this is just spinning discs, Tesla coil, and ultrasound. So everything minus the high voltage, because it makes it a little easier to see on the scope. 1, 2, I'm not trying to play around with the high voltage today. Well, in this particular test. Right now, I'm just trying to see if I can get the Tesla coil charge that is operating on all of these surfaces to be affected by the ultrasound frequency, which, if I start adjusting, if I adjust this down, you can hear the ultrasound is on. And I have found that at the very end where you can hear it, down there you'll get a slight interaction with the speed of the discs and the back EMF and all that we're seeing. And then another weird spot is somewhere towards the top end frequency of this thing, which is about 35 to 40 kilohertz, thereabouts. That up there, you'll actually see some stuff. And that one's really interesting because the power going to that piezo goes down as you turn up the frequency. And so it's like the minimum power input to it at the top end frequency. And that just so happens to be where you'll start getting some interactions. Very interesting. Sylvian, yeah. If you want to make the Graviflyer, you can DM me at mightybrain@yahoo.com, and I can shoot you a link for all of the parts lists that you'll need to be able to make this thing. So you can just, it's like following a recipe. You buy all the parts at all these different websites, and you can put it together, and got schematics and all that if you want to make your own. We are using 1 millimeter thick quilted aluminum or orange peel aluminum discs. That's the key words that they use for this special patterned aluminum. You can kind of see it on there that it's like rough looking. That roughness changes the thickness throughout the surface of the disc. So instead of being 1 millimeter thick, it's 1 millimeter plus or minus 0.1 millimeter, so 0.9 to 1.1 millimeter thick. And there might be some important things there. Alexey thought that it was better for holding more charge because the roughed up surface area, you got more surface area, so more places for the electrons to be stored. I've tested that, and I haven't really noticed much of a difference in the capacitance of rough versus smooth discs. But it's possible that like skin effect frequencies or something like that, where they're operating at a certain depth inside the metal, that might be important for why the rough discs work better than the smooth discs, because it kind of broadens your tuning range. And in the videos of Alexey, the middle plate really looks like wood covered with aluminum. I can assure you that Alexey was not using wood in any of his Graviflyers. He never used wood. We've spoken with him about this, and we bought Graviflyers from him. He never used wood. He did have a Graviflyer that the center disc, I mean, he gets all his parts from a junkyard, and the center disc that he was using had like this weird oil, like stuck on sticky oil stuff to it that wouldn't come off. And it looked like rust. For the longest time, I thought he was using like a steel disc or something, and that was rust. But no. It's not rust. It's not steel. It's aluminum. It's non-ferrous. No magnets stick to it. And that rusty-looking stuff was just oil. Jeremiah says, I'm waiting for the new piezo transducers to arrive later today for the Kedium device, which should be a more direct approach in researching the magnetohydrodynamic ion. I can't see that because the thing's in the way. Phonon coupling effect. That sounds interesting. I know KDM just posted a video. I haven't watched it yet. It was like 45 minutes long. Yes, our team is also looking at trying to replicate KDM's device. We will see how that goes. So, now that I got everything running, I'm going to turn on my high voltage. Hopefully it doesn't arc on me. I was getting it to spark really good last night at these distances. So I know that I cannot turn up my high voltage above a certain value without it arcing. Something else about Alexey's tuning procedure, he has shown that he was showing us that you have to very slowly, incrementally increase the high voltage. I've been testing around with that, and I go back and forth on it. For the longest time, I thought that wasn't important, but then he assured us that it was important because that's how you build these torsion fields up. You can't do it too fast. And then for a while, I was measuring with my static meter here on the discs and seeing that, yeah, it looked like it is slow to charge. But then I found a broken wire on my bottom high voltage wire. And now that I fixed that, I can crank up that voltage real quick and the voltage is there on the discs. So I've been playing around doing a little fast and loose and just cranking it up and observing changes then. Let's crank that up a little bit more. Please don't spark. Please don't spark. Shucks. My spectrum analyzer is screaming at me that it's got too much juice coming to it. Gotta adjust that. There we go. Let's fix our frequency on this. 7 megahertz. Stop frequency of 15 megahertz. Yeah, I guess that's okay. Amplitude. Zoom that down a little more. Make it a little easier to see maybe. So down here at the very bottom, I got my fundamental frequency. For the Tesla coil, which is coming out at about 740 kilohertz. And that frequency will change depending on the depth that you have the wire down the throat of the thing. I am capacitively coupling by just having a wire down the throat of the test coil without actually touching anything. And that seems to work well. It also kind of prevents some back EMF sparking that destroys the electronics. Alexey did connect his directly to the Tesla coil secondary wire when he would do outdoor testing, but when he would do indoor testing, he would just put it down the throat. Or maybe I got that backwards. Charles, correct me if I'm wrong. I think it was the other way around. I think he was connecting it directly indoors and down the throat outdoors. I don't know. Either way, he showed that you can get lift whether or not it's connected to the wire or it's capacitively coupled inside the test coil. All right. I think I am just about done applying my high voltage. All right, that is the absolute limit that I can get before it's going to spark, and it might still spark on me. Please don't spark. Let's check our voltages with our static meter here. So to use these static meters, you hold them 1 inch away from the surface, and you don't want to hold it like this, right? You want it to be parallel to what you're doing, and then if you can't do it edge on, you want it perfectly tangential like this. If you hold it at an angle, you're going to be getting kind of a less than accurate reading. So let's check the top disc. No, 1 inch is right there. All right, so we're at about plus 8 kV on the top right now. We're at about minus 9 kV on the bottom. And I'm at plus 1 on the center disc. So depending on your spacing of the discs, assuming all else is correct, the spacing of the discs, the offset of the discs is going to determine whether your center disc is getting positively or negatively charged. it's gaining a net positive or gaining net negative. It'll also determine your two discs, which one is a little more positive or a little more negative than the other. So once again, spacing is one of the most important tuning features in this whole deal. Jean-Paul is saying, why don't you stick with the original schematic? It could make the difference. So in some ways, I am sticking with the original schematic. So right now, I'm using the original schematic for the Tesla coil circuit and the ultrasound circuit. However, we have tested the original design multiple different ways and have determined there are some ways that it certainly could be improved. I wholeheartedly agree, though, that sticking to the original is probably the best chance of success because it worked for him. It should work for us, right? Well, some of his original schematics had issues. For example, he's using computer fan motors. And those computer fan motors have so short a lifespan because their bearings are so little. They're not designed to handle a load like this, especially a load that's like wobbling like that. So those bearings wear out really fast, which slows down the speeds of the motors, makes them less efficient, and makes it a lot harder to tune. So I think he could only get like maybe 20 to 30 hours of tuning out of one of those before they would start to poop out on him, which is not ideal. So that's one example. Another example would be, what would another example be? Oh yeah, so his discs, they're not like perfectly round, they're not like perfectly balanced and all that. And you can see mine aren't exactly balanced, but they are perfectly round. I got these things laser cut. Another thing that's different is his magnets. He's using Alnico. We think it's Alnico. We don't know for sure, but we think it's Alnico type magnets, and we're using neodymium. And the magnetic charge on his is about 1,000 Gauss. And part of the reason why it's that much is most likely because the Alnico, the ceramic, it's all cracked in all these different places on like all the magnets. And when you break a magnet like that, you're reducing its overall magnetic strength. So we're using about twice as strong magnets, which, once again, deviations, not ideal for replication. But at least this way, if nothing else, we find out what doesn't work. You know, there's no bad results, just null results. Sylvian, your motor spin at 2K RPM. If 6 magnets, it's 2K times 6 around a frequency of 12K. Does the frequency need to fit with the frequency on the plate? That's a great question. So there's, I don't like to think in terms of RPMs. My scope measures things in terms of hertz. So I just think in terms of hertz. It makes it a little easier. So right now I have these things spinning at 19 and 20 hertz, and 20 hertz would be equivalent to about 1,200 RPMs. I've observed in Alexey's videos that it seems like his discs are spinning very smoothly. And as you increase the speed of these discs, it'll start getting a lot gnarlier with the wobble. I will do that now to demonstrate. Hopefully. So you can see I got these black lines. I see if I can tilt it so you can see a little better. So I put like this framing around the edge of the top and the bottom of the disc, of the center disc, to try to reduce some of that vibration that's occurring right now. And then I clamped it down with these little 3D printed clips. But even with that, you can hear and see how much it's brrr. And Alexey's isn't doing that. Which that tells me that he's not running at these high speeds. I can turn this up even faster. and it goes away. Kind of. But it's going to want to come back. So let me turn off. That's, I can actually see the frequency now. I'm going to turn off my test coil and high voltage to actually see how fast they're spinning. All right, so right now I have the top disc spinning at 34.5 hertz and the bottom disc spinning at 28.8 hertz. 30 hertz would be 1800 RPMs. So I'm like, 2000-ish RPMs for the top and like 1700-ish for the bottom. Alexey told us originally that it needed to be like 2,500 RPMs for the bottom and 3,000 RPMs for the top. And there's no way that he is spinning his that fast. And then in a follow-up email that I sent him, he told me that actually you need to be running both of them at a combined 7,000. So 3,000 and 4,000 RPMs or 3,500 and 3,500. So he seems to think that the faster you spin the discs, the better. I have tested these things up to those speeds, and it is scary as all get out to have these little RC car motors spinning a spinning razor blade, a 200 millimeter, 300 millimeter diameter razor blade, a half a meter from my face. But yeah, I've tested those speeds, and the only thing I have observed at those speeds is just how insanely bouncy the whole thing will get. It's a little weird that he recommended those fastest speeds, especially considering that we have tested the Graviflyers he sent us, and granted, those have had some runtime on, right? Probably 40, 50 hours at least on those motors, and so the speeds have degraded, but the speeds on those motors is like in the ballpark of 600 to 1,100 RPMs, which makes a lot more sense when you watch his videos and see how smooth those discs are spinning. They got to be spinning at lower speeds. If you cover the aluminum plate with plastic or tape, eliminating discharge, anything like the near motor could probably help. That's what I will do. That's a great idea. So Charles, my partner, he has tried that in the past. There's this stuff called Kapton tape, Kapton, Kapton, and it's like high voltage tape that's really good for protecting against arcing and stuff. I don't want to put tape on this thing though. I don't know how much the electric field interaction is important. I mean, we got electric fields present, we got magnetic fields present. The Kapton tape isn't going to do anything to the magnetic field, but it is going to dampen that electric field interaction. And I have a suspicion that you need both of those interactions in order to achieve lift. So I'm not putting tape on anything yet. I may eventually in the future, but as of right now, I'm focusing more on trying to match all of the strengths of the fields and maybe somewhat the frequencies of the fields. Another thing about spinning the discs. So this bottom disc is creating an eddy current in this center plate, right? And then that eddy current is transferring to this top disc. So this top disc has a secondary eddy current from the spinning of the bottom disc. Well, because you have counter rotation of that top disc compared to the bottom, that means that the eddy current is going one way on the bottom part of this center disc, and then the top part of that is getting fought by the secondary eddy current. It's going backwards. So even though the eddy current is going one way from the bottom disc, it's kind of getting, the tip of it's kind of getting feathered back by the counter rotating secondary eddy current from the top disc. So you got a really interesting magnetic field going on in that eddy current in the center disc. Yeah, there's probably a there. My calculations for the magnetic field strengths and the speeds and all that, It's suggesting that the depth where that feathering occurs for that top part is probably somewhat related to the either the RF frequency of the Tesla coil, or it could be related to the ultrasound skin depth. I haven't been able to determine experimentally which one, but it looks like it's possible that it's one of those two things. Why does Alexey say he spins it at 2K? Like, I don't know. Alexey is not using measurement tools. The only measurement tools that Alexey uses, besides his ears and eyes, is he has this little gravitometer, which is a very simple circuit that essentially is just telling you that your electric field has reached at least, I think it's 1,000 volts. So that thing is the equivalent of this thing, but instead of costing $150 or $200, his costs, $5 or $10. Maybe the frame needs to be more rigid. I mean, my frame is more rigid than anybody else's Graviflyer out there, just about. You can see I got these 3D printed crossbars at the top and bottom. And then I have the same things on the top and bottom on the center disc. And I got this outside ring on the center disc. And then my 3D printed cross struts here. Those things are thicker and denser than what I was using in the past. Although I will say, Alexey uses aluminum cross struts, and those things are more rigid, and they're solid pieces. I have an articulation point on here so that I can slightly tweak the position of the two discs on the top and bottom relative to each other. I have tried, you can see up here in the corner, that was the first Graviflyer I built, and the center disc there is a pizza pan, and its thickness was 2.3 millimeters, I want to say. So it's a lot more rigid, and it's smooth on the bottom side. It's quilted on the top side of that center disc. But with that rigid structure, I will say I got a lot more pure musical tones at the perfect distances and speeds of the spinning discs. I get these pure musical tones that when I get them with this guy, they're much quieter and they're much less stable. They'll change frequencies a lot faster, and it's really hard to get them to be a stable, pure note. And when it is a stable, pure note, it's a very quiet note. Another reason why that might be the case is because this is, completely cut around the edge of this center disc, whereas that one you can see it's kind of rolled for the outside ring of the center disc. So it probably affects how it resonates there. All right, so let's go through a little more testing here. So I have turned off my high voltage and Tesla coil, so I'm really going to have to shut this thing down and start it back up from scratch at this point. And while I'm doing that, let me screen share some of the tools that I've been using. Unfortunately, I think I can only share one at a time. It's unfortunate. But if I hit run. All right. So this screen that you should be seeing right now, I hope. Let me make sure that it is screen sharing. There you go. So this screen that you're seeing now is a lab view screen that is connected to the oscilloscope. And now when I turn on the discs, I have to go back over here. That's auto scale. There we go. This. Oh. There we go. So now you can kind of see, and maybe I can even zoom in a little more. Now you can kind of see what I've been watching for most of my testing. You can see I got the 28.75, 20.7 hertz for the bottom disc. That's the red line. And then 34 hertz for the top line. And of course, I have it in RPMs over here on the side too, just so you don't have to do the calculation, which is 1700 and 2000 RPMs. But as I have now turned that on and we let it sit for a minute, you should see the speeds of the thing kind of change a little bit and start to even out until it finds its resonance points. Let that sit for another minute here. So what will happen is, when I put the high voltage on this thing, it's unfortunate. It starts getting really noisy, like you see these vertical spikes here. It starts getting really noisy like that. But if I zoom out, you can still kind of see the white negative space where those spikes reach down to. And so you can still kind of make out the general speed that it's at. You can tell when it's slowing down or speeding up when I have all of the high voltage present. Nathan's saying, on the top 3 inches of the Tesla coil, what frequency difference did you get? Oh, you mean like the wire dropping down the throat of the thing? For the length of the whole thing, when the wire is at the very top versus the wire at the very bottom, it's the difference of like, I want to say 40 to 60 kilohertz. I want to say I go anywhere from like 740 hertz up to 815 kilohertz. Yeah, 740 kilohertz to like 815 kilohertz is like the range of where you put that in. Now, with that though, you get a voltage difference. And I can actually do that right now and show it off. I'll turn on my test coil. So this vertical that you see on the test on the blue here, that is with my 1000x high voltage probe. So it's saying 42.4 volts on there, so multiply that. I think I have 10x attenuation on here too, so that should be equivalent to 4,000 volts. So if I take this high voltage wire, which right now is very far down, I can't see it. I got to tilt this so I can see it. There we go. Okay, so up the very top, sitting at 41.4. As I go all the way down, oh no! Ah! Catastrophic fail. Shoot. Apologies, folks. Let me wrap this back up and hopefully won't fall again. But yeah, actually, I wasn't seeing too much of a voltage change there, which was kind of odd. All right, let's try that again. Now, instead of voltage change, I will check frequency of the Tesla coil. So zoom way in. It's going to ruin my. It's going to ruin my lab view there, but that's okay. I'll bring it back. Measure frequency. There we go. All right, so at the very top, I have the wire set, so it's just barely in the top. I'm sitting at, I gotta stand far away from it so I don't affect it. I'm sitting about 866 to 868 kilohertz. Come on. There you go. So 866 kilohertz. Now as I grab this, will change. So I put that down there. You can see it's stretching out. How about I zoom out on that a little bit so it's a little easier to see. There we go. Now as I put that down the throat, you can see the frequency is stretching out. There we go. And now at the very bottom, it looks like I got a higher voltage. Now I'm at 47, so 4.7 kilovolts at the very bottom. And I'm sitting at, gotta stand away from it so I don't affect it. Now I'm sitting at 733 to 735 kilohertz. As I adjust the potentiometer knob, it doesn't really look like it makes a huge difference. Like, it's the difference of about 100 volts, maybe 200 volts for the peak to peak on the Tesla coil, which is nothing. The part where you really notice the difference, though, is the amplitude of some of these higher harmonics on the spectrum analyzer over here. If I stand out of the way. Some of these higher harmonics, especially around, like, I think it's the 6 or the 9 megahertz, somewhere around there, that harmonic will change a lot. The amplitude of it will change a lot depending if you go all the way up or down. Let's see if I can actually find that and zoom in on it. All right, well, right now the one I'm seeing is close to 14 megahertz, so let's zoom in on that. There we go. Let me zoom in a little more. Try to make this thing nice and big for y'all. All right, so it is jumping around a little bit. Let's see if I can average that out a little bit. Let's see. All right, now let's see if I can. No, I'm having trouble showing it on here because it's jumping around too much. If I zoom back out, though, I think it's a little easier to see. There we go. There we go. So now I have the thing cranked all the way up, and you can see we're peaked out up there. I think if I that, there we go. All right, so right now I'm at negative. When it's at its highest, it looks like it's about negative 51 dBm. When it drops down there, it's like negative 54 dBm. But when I adjust the Tesla coil now, now it is at negative 56 to negative 59, right? So I've lost about 4 to 5-ish dBm, which RF engineering, every 3 dB is double the power, right? So by dropping 6 dB, I've quartered the power. Anyways, so yeah, and that's at 14.6 megahertz on this particular setup, which, watch what happens as I adjust the, and just by me coming close to it, yeah, you can see it adjusts that. I hope that's shown up on camera good enough. But as I bring that up and out, now it's completely gone away. There you go. Now it's dropped down. So I said 14.6, right? Now I'm at 14.4 with the wire up near the top. So that frequency change down at the 740 to 840 kilohertz, that extends all the way up the frequency range. Let's go back down to 1 megahertz there. Fix this so I can see everything. Stop frequency 15. Yeah, okay. 15 megahertz. There we go. All right. Let me get back to some of these questions here. Increase your camera size to fill the bottom of the scope screen. Are you talking about this? I mean, I'm zoomed in as much as it'll let me zoom in on this. As far as on this guy, I can't really get the camera much closer without it getting affected by the high voltages present of the Graviflyer, which is unfortunate. Oh, get rid of the scope window. Oh, shoot. Yeah, I probably done that, and then you could have seen everything I was doing over here, huh? My apologies, folks. My apologies. I can zoom back in on that and do it again real quick so you can see. Let's go 14.8 megahertz. Let's go 14.3 megahertz. 14.6 megahertz. All right, that should be a little easier to see now that I've minimized the scope window. Thank you for reminding me about that. We can maybe fix this. Here we go. So right now it's kind of hard to see. It's down here. It's kind of quiet, but if I push that wire down the throat again. I'm having trouble seeing this. I see a lot more regular spikes, but I'm not seeing that 14 point. Oh, I think my stop frequency isn't high enough. There we go. There we go. I'm gonna do it one more time. So just me touching it, right, brings it down, right? Just bringing my hand close to the Graviflyer is increasing the overall capacitance, which is dropping the frequency. So I have to make an adjustment and then look at it again, right? So yeah, you can see the gist of it. So down there with the wire up at the top, the wire at the very top of the throat, we're sitting at 14.5 meg. Wire all the way down to the bottom. I'm seeing so it's 14.54 now it's 14.57. That doesn't seem like enough. Let me go down to the bottom. See if I can show you guys down here how much it changes. So this is 0 to 1 megahertz. I changed that to 500 kilohertz to 1 megahertz. Adjusting the knob, you can see from min to max isn't really affecting any of those amplitudes. Wire from the very bottom, right? So you can see that all these other spikes that I'm getting here, that's like radio stations and TV stations and stuff. Really, it's this spike here that we care about, which is 759 kilohertz. All right, so it was 759 at the very top of the throat, at the very bottom of the throat. We're sitting at 728. So yeah, it jumps all over the place, guys. I don't know. I just want to keep testing. On the subject of divergence, have you tried using rotors with different diameters? Do you mean different diameters like both rotors are larger and smaller, or one rotor is smaller than the other rotor, or one rotor is larger than the other rotor? Because I tried both. I have tried both. Right now, these rotors that I'm using are slightly larger than what Alexey used. So Alexey used imperial units, inches. He used like 7.9 to 8.4 inches, right? In millimeters, that's like 190 to 230 millimeters, right? So right now, I'm using, I think, a tiny bit more than 9 inches, which it's like 230 to 250 millimeter diameter spinning discs. And then one of the things I'm keeping the same, though, is in all instances, he always had the center disc exactly double the diameter of the spinning discs. What are the insulators on the big disc for? That'll change the frequency too. Insulators. Oh, nothing is actually insulated on the center disc. The plastic that you're seeing is just structural support to prevent vibration of the disc. But electrically speaking, everything seems to be about the same as it already was. The center disc is still electrically shorted to the vertical rods, and I'm running the Tesla coil onto one of the vertical rods. Yeah, so let's do some rounds of testing here. So the first thing you do is you get the discs up to speed. Once they're up to speed, then you can turn on your Tesla coil. Once your Tesla coil has been turned on a while, and the speeds of the discs have adjusted for that, then you turn on the high voltage. See if I can zoom back out on this and be able to use that scope window that I was using. It's not going to be super useful, but it will provide some value. All right. It's so little power from the test coil. I don't see how I can do any lifting. Sort of, kind of. I mean, if you combine all factors together into power, then yeah, it's not a lot. But if you separate them into voltage versus current, it's got, a decent amount of voltage. It's got 4 kilovolts coming to it. And then you combine that with the high voltage that we have present on the spinning discs. You combine that with the magnetic field strength that we have present, which, how would I show that? So I have a magnetic field meter here. I'm going to get you guys some numbers for the magnetic field strength before I turn on the high voltage to the spinning discs, which will certainly make it more difficult to test with this guy. But let me peek. There we go. So right now, at the surface of the top side of the center disc, I'm at 1.94 millitesla, or 19.4 Gauss. And then on the bottom side, Don't touch the metal when there's Tesla coil present. It shocks. All right, so at the surface of the bottom side, I'm at 20.7 Gauss. But as you get closer and closer to the magnets, yeah. Let's see if I can test this without doing my. Yeah, we're like 100 Gauss. Yeah. Anywhere from 80 to 100 Gauss at the surface of the magnets. So, I don't know, electric and magnetic interactions causing forces of wobblage. Yeah, I don't know how the force diagram for every small part of this works because you have so many third and fourth order interactions going on. It's really hard to keep track of. Hopefully the console guy finishes up this stuff soon. Let's see who's saying what. Todd is saying the difference from 937 kilohertz to 750 kilohertz is probably only 5 watts DC. Well, I can actually see on my power supply how much power the Tesla coil is drawing. I think I have the wire all the way down the throat right now, and I'm sitting at 6.9 watts. So bring the wire all the way up to the top. Now I'm at about 5 watts. So, good guess, Todd. It's 2 watts difference from that top to that bottom. That's saying 4.8 kilovolts right now at the top. What's it saying at the bottom? .66 kilovolts at the very bottom. I don't know. I like to have the voltage. Well, I guess it's better to be drawing more power than it is to have slightly higher voltage because if you draw more power, that's more place for power to go. No, I haven't measured anything with the gravitometer right now. I was saying, though, how the gravitometer is essentially just a tiny little analog multimeter with a 1,000-volt capacitor attached to some metal plates. So all it's doing is it's measuring when the difference of potential of those 3 metal things has reached about 1,000 volts, which that's just an electric field meter. I have a much better electric field meter that I'm using. So I would rather use this than his gravitometer, although I will probably eventually use the gravitometer, but for now, I'd rather get accurate numbers rather than just a blinking LED light. So, for example, I can hold this thing about where you hold the gravitometer, and I can see I'm at about 0.4 kV. So I need to be at least 1 kV, around here for it to be able to turn on the LED for the gravitometer. You might want to move the other Tesla coil away from the one you're testing with. Anything your Tesla coil will draw power from, so everything 2T. That is a really good point, Trolls. Thank you. Thank you. Thank you. Bring you away. Bring you away. Maybe even scooch you closer. Don't fall. All right. unnecessary electronics from the mix. There we go. All right, and now I've gone down in power requirement by about 100 milliwatts. So that was a good call, Charles. Thank you. What if you pull it all the way out? Pull the wire all the way out of the test coil. See if I can do that without shocking myself. All right, with the wire completely removed, the test coil is drawing 4.1 watts. And my frequency is 962 kilohertz, which is, I think, close to what you measured on yours, Todd. In that, just sub 1 meg range. Let me make this a little easier to see again. Yeah, Charles actually built this Tesla coil for me, and he also built one for Todd. He built the circuits for us too, and Charles does awesome design work because you see the similarity between what Todd is saying he got on his and what I'm getting on mine. So let me put that wire back in before I forget, so that I can continue on with my testing. I suspect probably the winding of the primary on the Tesla coil is another important consideration when thinking about the depth of that wire down the throat. Probably couples a lot better when the wire down the throat is actually in the magnetic field of that primary winding. All right, let's see. I am probably ready to turn on the high voltage DC, but first let me go back and it's going to do it. Go back and start sharing this guy again. Is it sharing? Window. This. Oh, there we go. There we go. So you can see, like, my blue line for the top rotor. It disappears. LabVIEW is actually free, Nathan. The tricky part is getting it programmed properly to talk to everything, which Mark and I found this programmer who ended up programming all of Mark's stuff, and he ended up programming all of my stuff. And I want to say it took about 2 to 2.5 weeks of working together. Like, you have to be there and present with him and like turn on, turn off, like connect stuff. But yeah, it's all specific to which scope you're using and how you connect it to your computer. I have all of my stuff connected via USB, which is a lot easier than connecting with like GPIT connectors or IEEE type connectors. Like, USB is so much easier. The problem is that I think it's a little more susceptible to noise, which is a problem. Anyways, so right now you can see that I'm sitting at 28 hertz for the bottom disc. If I zoom out here, you can see if that's changed at all over time. So here you can kind of follow how that line has been changing as I've been, tweaking and adjusting things. And even if I wiggle the Graviflyer, that speed will change. But this is a very useful tool because I can see when I make a small adjustment if it ends up shooting off like that. Yeah, the Tesla coil wire right now is, so right now the secondary winding of that Tesla coil is around a plastic tube. And then the wire that I'm using is it's a clip, which is completely insulated. So like there is nothing for it, nothing metal for it to make contact to. It's not making um, any electrical contact. It's only making electric field contact. All right, so unfortunately, I can't really show the blue very easy. Maybe I can. Nah, you can see it's so painfully noisy. I'm losing out most of my blue right now, which is the top rotor. And that's only going to get worse as I turn on the high voltage. So I'm just going to watch the bottom rotor. The two rotors are coupled, but the top rotor is the more sensitive rotor to changes. So it is unfortunate that I'm not able to view that at the moment. But nevertheless, let's turn on my high voltage. Just going to crank it all the way up to the top. Don't spark. Don't spark. All right, I'm at 16 volts in to my flyback circuit. Right now, this present setup, I have observed that it sparks at about 16.4 volts in. And part of that is dependent on the Tesla coil power, right? The voltage of the Tesla coil is creating an additional difference of potential. It means that it might want to arc on me. Anyways, I'll leave that on here for about 3 or 4 minutes to let speeds kind of equalize out. While I'm doing that, I will zoom out on this, turn off my average. What I want to show you guys is these pulses and how I can get these pulses of the beat frequency to change with the ultrasound adjustments, which hopefully we'll be able to notice some kind of change. Oh my God. Oops. These noises with the high voltage on, it makes it impossible. Nope, I am not using the gravitometer today. The gravitometer is a static field meter. It is just metal attached to a 1,000-volt capacitor, telling you if you have a 1,000-volt electric field. This thing can tell me if I have up to a 20,000-volt electric field, so far superior. Yeah, it's not telling you anything about the magnetic field. It's not telling you anything about the frequency. The only thing the gravitometer is telling you is your electric field strength. All right. I think we should be good for the high voltage. Now, something that Alexey does not do, that I've been doing, he does not adjust the speeds of the discs at all. He like sets them at the beginning and leaves it. And I think part of what he's doing is, in addition to controlling the voltage difference, like I said at the beginning of the whole thing, the slight difference in distances equates to the difference of potential that the two discs are putting on the center disc. In addition to that, the distances of the discs are affected by the magnetic field, the eddy current, which is also causing drag. So he's adjusting the speeds of the discs, slightly adjusting them by the Tesla coil and the high voltage and the ultrasound. So what I've been doing instead is I will make slight tweaks to the speeds of the spinning discs and try to observe on my scope if I can get them more balanced, right, more in the ballpark at the proper speed. And then once they're steady there, then I go to my ultrasound and my Tesla coil and start tweaking those to see if I can adjust the speeds that way. So I'm hoping that by identifying the proper frequencies and settings and everything to adjust speeds. If I'm adjusting speeds, to me that says that I'm getting close to actually achieving lift, because I'm increasing the number of interactions present, right? Wookie, I am using this quilted orange peel aluminum stuff, which is the rough discs that Alexey uses. I am using that for all 3 discs right now. So all 3 discs are cut from the same sheet of aluminum. It's 1 millimeter thick, and the diameters of my things right now are like 9.2 inches diameter, I think, for the spinning, and then like 19 inches diameter for the middle. The middle is exactly double, so it's got to be like 9.5 inches for my spinning discs, something like that. Anyways, let me get my scope zoomed in here so I can see what kind of speed adjustments I need to make. And while I'm doing that, I will move that so it's a little easier to see my spectrum analyzer. Daniel's saying someone out there made a scalar detector. Yeah, you should share a link to that. That would be pretty cool. I'm almost done adjusting the scope to make it more visible. All right, you can kind of see these spikes that are moving around on there. And right now it looks like they're traveling up. If I zoom out, it'll look like they're traveling the other way. Now it just looks like chaotic noise. So what I do is I just pick a setting where they're moving slow enough and in a certain direction so I can see what tweaks I have to make to the speed to be able to get it to properly adjust the speed of those spikes. So I'm increasing the speed. I'm also using my ear to hear if it's getting smoother. All right, now the spikes have started going back the other way. So I overshot. Slow back down. I don't know if you can hear that. It's a very quiet singing note sound. Adjust the speed down again. Watching my spikes. All right, they're starting to slow down. We're going to reverse. Okay, now I'm starting to reverse. Let's speed back up just a little bit. So eventually what will happen is I'll do this and I'll go back and forth, and eventually I'll get these guys to kind of like stay in place, but they're still kind of going up and down, right? You still get oscillation of the speed. I think I can get that just a tiny bit steadier. I'm increasing it like 10 millivolts at a time, which right now I'm using about an amp, so 10 milliwatts. It does not take much. That's probably going to be just right. Maybe? That's part of the patience for this thing is you make a slight adjustment and you gotta wait and wait and wait for everything to kind of balance out and even out. Looks like I might need to dial that down just another smidge. There, that's probably going to be money. I'm fairly happy with that. Zoom back out. So zoomed out, I can see that I'm still traveling, but I'm not going to be watching that while I'm doing my adjustments. It's more just about trying to see interactions than anything else. Let's see if I can average that out and watch it. There we go. So now you can kind of see a little bit of traveling going on. Let's see. Reading comments, what are we seeing? Oh, Daniel Foster. If you want to learn about the Hanabu, there is no better person to look at than Mike Gamble. I suggest looking up Mike Gamble's APEC talks on it. That man has spent the better part of like 30 or 40 years like researching the Hanabu craft, and he's like a master electrical engineer. So he's come up with not just how it works, but like very detailed electrical engineering-esque ways that it needs to be done, like what lengths your conducting antennas need to be, and what frequencies they need to run at, and what power levels and how much it weighs, and like start to finish, the guys come up with it. That's actually something that I might end up trying sometime down the road, is trying to build his idea of a Hanabu-esque craft. The problem is that for a 1 meter wide disc or ring, it takes like, what was it, 140 or 240 megahertz and like gobs and gobs of RF. Like you need kilowatts of RF to make the thing lift. It's crazy. Monitor test coil power while adjusting the ultrasound. Oh, I have done that, Todd. And unfortunately, I never get anything more than about, I don't know, maybe 10 to 20 milliwatts change on the power for the Tesla coil from adjusting the ultrasound, which is unfortunate. Yeah, that's like the main thing I do is I watch my power on the Tesla coil and I watch my my RF to see if there's any additive or negated power at any of the resonances, any of the resonant frequencies for the Tesla coil from adjusting the ultrasound. Um, yeah, and I'll show here in a little bit. I can zoom in on this, and you can see how adjusting the ultrasound, you can overlay it, you can add power, but the amount of power that you're adding to the frequencies of the Tesla coil is not much. It's not much. Um, the most important thing is that when you hold down the button for turning off the ultrasound, when you open that circuit, there's a sweep that happens, and I will show that here in about probably 5 or 10 minutes. Daniel Foster saying he saw Hanabu up close in an underground army base in Nordhausen. I would love to know more about that. I would be super fascinated to know more about that. Was it hovering? Can you at least tell us, was it hovering, or was it like being held by a crane or something? Like, was it lifting under its own power, or was it just there for reverse engineering and getting taken apart in pieces kind of thing? Let's see what else we got. Oh yeah, Gerald's here. What's up, Gerald? Oh, good. You did see Mike's breakdown of the Hanabu craft. Yeah, Mike is a smart cookie. He's got a lot of interesting ideas out there. Gerald is saying, are you searching for the Doppler effect when it comes to sound? Not exactly. If anything, I'm searching more for the Doppler effect with the RF because I got these chirps moving, right? And when I hold down the button, there's an upsweep in frequencies, kind of like an up chirp. So in that way, those chirps of frequencies that I can't hear are Doppler shifted frequencies. All right. I think I am ready for ultrasound now. All right, so I just turned on the ultrasound, and the direction is now changed, right? I'm going to adjust my ultrasound frequency so you can hear it. So that's minimum frequency. Slowly increase it. That's actually increasing it very fast. It's very slight adjustments. That minimum frequency you heard is like, I can't remember if it's 7 kilohertz or 17 kilohertz. I don't have a good way of observing the frequency of the ultrasound at the moment. Oh, I can, but I have to adjust everything. I don't want it. All right, so just by turning on the ultrasound, though, now our sweep has changed, right? And if I turn off the ultrasound, I want to say it should come back. It is not equalizing out. All right, I gotta tweak the speed again. Tweaking the speed to get those chirps to hold steady, or at least be moving really slow. It slowed down a lot. I wanted to switch direction though, because when I turn on the ultrasound, all the sweeps were going this way, but I turned on the ultrasound and they started going that way. So I want them going this way again. I want to replicate that again. All right, there we go. Chirps are steady. They should start moving the other way a little bit. All right, they're moving this way very, very slowly. And I turn on the ultrasound. Chirps increase their speed this way just a little bit. So the speed of this, like I said before, the speed of these chirps is directly proportional to the beat frequency between the two discs. So the beat frequency of the discs changes when you apply the ultrasound. Okay, now the chirps stop moving. They're pretty steady. Turn up the frequency. See if I can get the chirps to move. This is the tedious part, is ultrasound frequency adjustments. All right, now I got a single chirp slowly moving back. Right here, it's moving back. Here's another one. All right, so now I've adjusted the frequency. I've gotten the chirps to go from moving this way very slowly to steady to now they're moving this way. Keep increasing the frequency of the ultrasound. All right, now the chirps are speeding up as I go up in frequency. So the ultrasound, it kind of dampens the vibration, especially at the top disc, which if you dampen that vibration, now you're affecting the beat frequency between the two of them, which means you're affecting these chirps, right? As you reduce the vibration, it allows for smoother operation, which allows for faster movement of these chirps. Daniel's saying that the Hanabu he saw at the Army base was on jacks with the Knight's Cross still on it. The Knight's Cross? What? The Hanabu I saw was over 100 feet wide? Jeez, that's a big one. That's a 30-meter craft. I want to say they come in 10-meter and 30-meter. And then like 100-meter. So yeah, that was a decent sized one. What's going on, Isaiah? Sounds like 17 kilohertz it was singing. Yeah, no, I think you're right. I think it was 17 kilohertz for the minimum. I've observed some interesting characteristics around the 23 kilohertz mark. Let me see what I wrote down. At the 15 and 23 kilohertz, that's where the ultrasound will overlap with the Tesla coil when I push down the button, which now is as good a time as any to show you that. So frequency 1.5 meg. Let's do this and zoom in more. Amplitude. There we go. All right. So now when I hold down the button, I gotta turn my attenuation down. Turn my scale back up. Okay, so I have to get more power in here. What's going on? Oh, it's because I don't have it connected to the right thing. Sorry. One moment. Oh my God. there. Nope. Hold. There we go. That's annoying. All right, so now I have the scope set up to the ultrasound here, the transistor of the ultrasound. You can see how at the lowest frequency, you get more amplitude. As I turn it up, the amplitude drops, right? The interesting thing is when I hold down the button. Here we go. So no button, turn that up. There's certain spots where it seems like it overlaps very well and actually will lock into the Tesla coil frequency. Like that. See how I'm just holding down the button, I'm not doing anything else. You see how all of these extra yellow in there, if I slightly adjust it, those go away. But there's a sweet spot there where it'll lock in. I can adjust it again and bring that back. And, whoa, look at that, right? So, zooming out on that, it gets really cool up around the 6 to 10 megahertz range. Up in here. I want to say that's what it was. Maybe not. Maybe it was down lower. My bad. So what I'm looking for is that Tesla coil frequency down here. That's annoying. Stop frequency. Is that? Yeah, that's the one. So what I have to do is I got to zoom in on this. There we go. So now what I'm going to do, I'm going to show it to you over here on the oscilloscope. Can I show both at the same time? That would be so cool. So cool. Turn off everything else. Let's make that brighter. Actually see it. And let me make it bigger. All right. Zoom in even more. I'll tell you what my settings are once I get this set proper. I gotta attenuate that guy. Oh, come now. Fine, we'll do that. You gotta zoom out a little more. Thank you for your patience, guys. All right, I don't know how well you can see that on the, yeah, you can kind of see it pretty well on the camera. This is the lowest frequency. I hold down the button. You don't get much change, right? As I turn it up while holding down the button, right? You can see all those extra frequencies you get, which right now, let's get some measuring going on. See if I can actually register that frequency. All right, so right now it's registering it at about 34 kilohertz. That's not right. That's audible. So half that. 17 kilohertz probably. Yeah, it's jumping all over the place because we got so much EMI everywhere. The gist that I'm trying to get at is that I think the sweet spot, if you can kind of see, let me zoom in on that more. You can see these blue, which this is coming off of the test coil, right? So I think by holding down the button and getting those spikes about the same, I gotta get my trigger fixed here. There we go. Now I can kind of try to adjust it and get those as close as possible to those test coil spikes. And in response to Todd's question, right now when I push down the button, for what happens to the power of the test coil is it kind of oscillates. So it looks like I get an initial drop and then it jumps up and then it comes back to medium and it stays medium. So there's definitely a timing to how long you hold the button down for. Anyways, I prefer to watch my spectrum analyzer. See if I can zoom in on this a little more. Right, and I try to set it so I get maximal power. And then I switch over and I see if my RPMs have changed at all, which we've already seen how well that's working. Window share. Yeah, let's small. Okay, so you can kind of make it out up here because I sped up the whole thing. It's sitting around 29.4. Oops. You can kind of see it, and it looks like the speed has kind of come up a little bit for the last few minutes here. Let's see if I can get that a little better. There you go. You can kind of follow like the middle of the noise there. It is definitely on my very near-term to-do list to fix this noise issue if possible, so that this program is actually useful. Because talk about frustrating. It's such a useful tool up until it isn't. Okay, there's another tool I'll show you guys here. That I've been using. I said, I thought I would show it. It doesn't look like it's going to let me. Okay. This might go horribly wrong. Let's try. There we go. You should be able to see that. This is my Spectrasizer audio, so you can see how it shows up when I'm talking. So what I do is I look for these spots where it's a solid frequency, right? And I can use this with the test coil or with the ultrasound. This is another way of seeing what frequency I'm at. And here you can see I have harmonics going on. And you can see that the higher harmonic has much less power than this lower harmonic. And I don't know what is causing this this solid line over here. It's like 20.2 kilohertz. I don't know what causes that. It's like the motors or something. Anyways. But there you can see the red line, meaning it's a very loud signal. More harmonics. There's probably an important feature of these harmonics that is coming into play with the Graviflyer's operation. Anyways, one other thing I want to show you. When I hold down the button, look at that. I'm still getting the signal with the button down. So while holding the button down, the button is still held down, and I'm adjusting the frequency. Anyways, that's there's probably a there as well. Anywho, yeah, I don't know what else to show you guys today. I did want to show you, there's one last thing I want to show you guys if I can find it. I might not be able to find it. It's an ultrasound adjustment position. All right, like that. Where we can actually see the Tesla coil coming into play. I feel like it's quite important. Let's start frequency down here. So it's not really picking up the Tesla coil right now because I'm plugged into the transistor on the ultrasound. Maybe it was on the scope over here. I don't know. Maybe I won't show you guys. Yeah. Zoom way in on this. I'm gonna zoom out on this guy. Zoom in between them. Yeah, no, I'm not finding it now. Never mind. I'll have to show it next time I do one of these live streams. Yeah, how you guys liking the once a week thing? I might do it every other week. I don't know. I'm up in the air about it. Let's see what I have missed on the messages. 23 kilohertz and 17 kilohertz is where we want standing waves, but we also want the solfeggio close to 7 point something hertz. Yeah, if we go off of Mike Gamble's idea of the Schumann resonances being related to gravity, I think jury's still out on that one. I'm also not quite sure about that because, like, you can look at planets that don't have a magnetic field, but we still know what their gravity is. So, like, Mars doesn't have much of a magnetic field, and so it doesn't have much of an ionosphere, and so it doesn't have much of a Schumann resonance. Like, it's got 1% the Schumann resonance like intensity that the Earth has, and yet it's got, like, what is it, a sixth of the gravity, a third of the gravity, something like that. I think it's a third of the gravity. So, like, if that was the case, then you would think that I don't know, and like asteroids or any body that has either an extremely strong or a non-existent ionosphere and thus Schumann cavity, you would think that we would see differences in like their orbital patterns and stuff, and we don't see that. So I keep bugging Mike to run his numbers again for any other body than Earth and see what comes out from that, and see like the moons around any of the other planets, right? See if their orbits line up with any of those Schumann resonance wavelengths. And I think he just hasn't gotten around to it yet. But I think that in order to actually like provide more validity to his claim, he needs to do it for more than just Earth. He needs to do it for another body for which we have enough data to understand what Schumann resonances it's operating at. And also Mike Gamble thinks that it's the third harmonic of the Schumann resonance. So that would be like 21.4 hertz or something like that. Which just so happens like that is in the ballpark of what we're supposed to be spinning these discs. So maybe there's there. I don't know. Todd's saying, I keep looking for a frequency that won't stop growing in amplitude. Yeah, like, there's a couple of spots where it'll grow in amplitude up to a point, but not much. And I think the amount of amplitude gain that you get there is going to be highly dependent on the spacing of the discs, as well as maybe the speed of the discs, but especially the stability of the discs, right? If the discs are wobbling too much, that'll increase your chirp amplitude, but that'll decrease your the resonance of your cavity, and so your overall gain from the ultrasound, I think goes down. So yeah. But then again, like Alexey, we measured the wobble on his discs, and it's like plus or minus 3 millimeters or something like that. It was plus or minus 1.5 millimeters. Anyways, it's a decent amount of wobble. On mine, right now, it's going like plus or minus, I'd say about 3/4 of a millimeter, plus or minus 0.5 to 0.7 millimeter for the top disc. Plus or minus 0.5 millimeter. But like there's speeds on here where I can get it to really wobble. And I've gotten it at like 6 to 8 millimeters, so plus or minus 3 or 4 millimeters, like Alexey's, which, I mean, now you're talking about gyroscopic forces that might be contributing to something there. I don't know. right? So that amount of wobble, should be able to show it on here. Oh, I'm not connected to. There we go. So I think that the amplitude somewhat increases when you get that much vibration and wobble. Maybe I'm just seeing what I want to see. So if I take these clips off, you can really see just how much wobble I get. And how loud it gets. I mean, these crossbars are still like preventing some vibration, like they are damping some vibration, but the more this thing vibrates, the more that thing vibrates. Yeah. I was observing some changes on here from the ultrasound initially, but also I think I don't wait long enough for the speeds of these discs to even out before I start messing around with the ultrasound. I need to learn patience. I'm too impatient. Let's go fishing. Fishing teaches a person patience. Anyways, I think that's all the testing I'm going to do on the live stream. I'll keep testing more tonight, but that's all I'm going to do on here. Let's see if I can answer any more questions here. Todd saying I tested spinning magnets and high voltage discs and didn't see anything. I'm more interested in test coil and ultrasound combination and looking for very large resonance. Todd, I will say that when I was using the signal generator with the old one back in the day, I did notice I was operating at like 4.7 megahertz input from this guy to the piezo. No. Sorry. I was using this for the RF. I was using this instead of the test coil. And I was doing 4.7 megahertz into an RF amplifier into the center disc. And I observed that the third harmonic at about 14.3 or 14.7 megahertz RF to the center disc, it caused the ultrasound at 63 kilohertz caused the third harmonic of the RF off of the Tesla coil to drop by 3 dB. So that was one of the first interactions between ultrasound and RF that I saw. Since then, since switching over to the Charles/Alexey circuitry, I seen some interactions between the Tesla coil and the ultrasound, but mostly it's like overlapping frequencies when you have the button pressed down. So when you push down the button of the ultrasound, and you get this upsweep in frequencies, which maybe I can show that a little easier on here now that things are turned off. That's steady. There we go. So now you can really see this guy, right? And when I push down the button, there's a moment where it squeezes together. If I zoom in more, it's up here higher. There's about a 1 second delay from the time that you push down the button to the time that the frequency of this is done changing. So in this case, I push down the button, and it starts at 37.3, and it ends at 38.3 kilohertz. And as I turn this up more, well, now I'm not seeing it. And zoom in more, make it bigger. There you go. Now I'm getting 48 to 52 kilohertz, but you can see the amplitude is such poop on it. I can try to increase my voltage a little bit, but I don't got much play on this ultrasound circuit. It actually will collapse it. The transistor will like stop working if you go above like 5.5 volts on there. There you go. Now you can kind of see it coming in. See if I can fix that trigger. There you go. There, that's what I've been trying to show. So press and done. Press and done, right? So there's a delay there that's pretty important probably. Because Alexey, when he presses the button down, we've like frame by frame counted and asked him, and he says, or in the frame by framing, like we've counted it somewhere about 300 to 400 milliseconds, right? A third to 0.4 seconds is how long he'll hold it down for, which that's just long enough for it to like sweep up frequencies. So don't doubt Alexey. Even though he doesn't measure anything, he always seems to have a pretty decent idea on what's going on. Yeah. All right, any last questions? Let's see. Yeah, Daniel, you should totally make the Graviflyer kit. I know you know. Oh, Sylvian's saying, I suspect that if your Graviflyer is on the ground or table, it's more stable and more easy to get the effect since it's like attached on the top and you get a lot of vibration effects. Hard to get. You can look at some of the older videos that I posted. One of the most interesting ones I have, I think it's got the word counter rotation in the title or something like that. And I have it sitting on the ground. And just by adjusting the Tesla coil, I get the thing to go from shaking like clockwise to start shaking counterclockwise, which means that the eddy current drag or the electrostatic drag has now changed just from changing the frequency of the Tesla coil. The problem with testing on the ground, though, is that these metal legs screech on the concrete floor, and it is so painful. Like, you can't record anything audio, which ruins my microphone software stuff that I was using to see what special frequencies or sounds we're hearing. That's one thing. Another thing is that when it's jumping around like that, all the wires want to start getting twisted up. Yeah, it severely limits a lot of your testing. I may end up going back to testing on the ground some, but for now, I'm probably going to just keep testing up in the air. And to ground the whole thing to ground, I got a wire here that is connected to my ground that I can just clip on to the leg like that. But I've observed that when I clip on the ground wire, that my center disc, right, it loses that offset that you get from the difference in distances of the charged discs. And in Alexey's, like, he's not clipping a ground wire, it's sitting on a concrete floor, so it's probably grounded, but the moment it lifts up off the ground, it's not grounded. So yeah, I don't know. Let's see. Todd's saying, my point is, it doesn't draw enough power to have lift. Yeah, no, like, absolutely. Somehow Alexey is getting this thing to lift off the ground with like maybe 15 to 50 watts of power, right? Middle of the road, call it 30 watts of power, which is like, it hurts to think about that's somehow possible. But RF mixing, magnetic electric field mixings, angular torque, right? Angular momentum gains or losses. I don't know. It seems like there's not one thing that's happening to contribute enough energy for lift. It's like it might be contributing lift in a bunch of little parts, and all those little parts are all stacking up to eventually produce enough. But even still, yeah, the overall power requirements for this thing to lift makes it quite crazy. I want to say I did the math for it back in the day, and it was something like, I thought it was more like 150 watts per kilogram that he was using, but I might have been using the wrong numbers when I calculated that back in the day. Alexey is using, let me see if I can show it on camera here. This is very similar to what Alexey is using. It is a ferrite torus with double windings on it, right? So it's just a transformer. And then you have a little transistor in there and a little 10-turn, I think it's a 10K pot with a resistor attached to it. And so you're just adjusting the frequency of the piezo buzzer via the windings on this. And I'll have to go back and look at it. I think it's 22 and 11 turns, 11 turns for this larger gauge, 22 turns for the smaller gauge. And the smaller gauge is what is going out to the piezo, I think. Yeah. Oh, no, the larger gauge is going to the transistor, and then, yeah, the smaller gauge is going between the 10-turn pot and out to piezo. He's not using an audio amplifier. Pavana is saying, while it won't be part of Alexey's original design, would adding a second set of magnets aligned as a Hallbach array amplify something that remains difficult to observe? That's a great question. So I bought lots of magnets to play around with different magnetic fields. One of the first things I did was I took one of the discs, and instead of 6 magnets, I put 36 magnets, right? I squared it. And And when I spun this up, and these are all like, I think I alternated in 42, in 52, in 42, in 52. But the difference was only like the surface magnetic strength on each one of these was like 2,400, 2,500 Gauss. So it was really close between all of them. Anyways, when I spun this thing up, the center disc vibrated so much more, and it took so much more juice because now you have a constant magnetic field. Yeah, I think one of the next things I'd like to try, a couple things I'd like to try. I'd like to make it a spiral pattern of magnets, right, in the direction of spin. Another thing that might be worth trying is much smaller spinning discs, and have all of the magnets, you know, around the edge of that much smaller disc. So all these, this overall magnetic ring is now much tighter magnetic ring. So your overall magnetic flux in the center there is greater. That might be another interesting thing to try. Yeah, a Hallbach array of magnets is on the to-do list, hopefully, eventually, maybe. But for now, I'm really just focusing on trying to replicate Alexey's original thing. I've spent like the last year-ish trying a bunch of new and different things, and now I'm starting to go back more towards the original. More Blow is saying he knows about the T.T. Brown stuff. Yeah, if you wanted to understand more about what this thing is and how it's working, I would recommend, first, I'd always recommend watching APEC videos. Like, you can get quite the education by watching some APEC talks out there. Not all APEC talks are the same, but if you just like set aside enough time to start going through all of the old ones. I think we got like 1,000 hours or more of APEC talks. That's if you got a lot of time on your hands. If you don't got a lot of time on your hands, you can watch just Alexey's videos and start learning more about it. You can go back and watch some of my older videos about it. I've talked about this thing ad nauseum. But yeah, without some basic electronics understanding, it's going to be kind of hard to understand because, you know, right hand rule, you know, when you have a magnetic field and an electric field, that means that you're going to have a force vector in a certain direction. Like that sort of stuff is important to know, or the current in a certain direction. Anyways. Does Alexey use any tubes in his equipment? Nope. Alexey's never used any tubes. Everything he's done has been solid state. Do you ever try anything around 28 kilohertz? That's a great question. All of my calculations suggested around 27.4 kilohertz was going to be a lot of sweet spot stuff. And I have observed some pretty good vibration damping around that with the old one. But now that I'm using greater diameter discs, that frequency doesn't work as well anymore. I think the new frequency that works now is like 26 kilohertz ish. Yeah, I need to go back through and do my piezo buzzer measurements on just the discs to see where their new harmonics are lying. Oh, and let's see. More Blows asking, who is Alexey? Alexey Chekurkov is the inventor of this. If you go to, like, I think I even included a link in the description of this. You can watch Alexey testing this device. My partner Charles made a compilation video. For anybody who doesn't know who Alexey Chekurkov is, check out the description of this chat and follow the link to the compilation video, and you will get a great rundown on what this thing is and what it looks like when it works. All right. I think that's all we got today, guys. Thank you for joining me for the Graviflyer Q&A and testing time. Yeah. Peace out, guys.